In this video, we will look at the backpropagation algorithm which are used for training recurrent neural networks. So let's get started. Backpropagation for recurrent neural networks. So the backpropagation algorithm that we'll introduce isn't really fundamentally different from the regular backprop that we have seen for feed-forward neural networks. But in order to apply it to these networks with recurrent cycles, we'll see that we get a somewhat different computational graph. And therefore, also the computations will be slightly different. Okay, so the algorithm that we'll introduce is usually referred to as backpropagation through time. Again, it follows the same logic as applying the chain rule in a systematic way to our networks in order to compute the gradients of the loss with respect to the different nodes and parameters in our computational graph. So we'll introduce this in the context of this little example network that you see here. So here we have some inputs X being mapped through the weights U to our hidden states H. Then we have a recurrent connection mapping H to itself at the next time step through the weights W. And H is also then here mapped via the weights V to the output O. And the output, as you can see here, is mapped through a softmax to the final output Y hat at time step T. So this thing goes into then again a loss function L together with the correct labels Y in order to compute this loss here. Okay, so in order to apply backprop now, what we do is we unfold this graph on the left as you see on the graph here on the right. So now we have this feed forward component of the graph at each time step for t minus 1 plus t plus 1 in this case. So just on the left, but we unfold the recurrent connections W over time, as you see here in the forward direction. So we have, this information going this way, but we also have the information that is flowing this way to the outputs. Now, what we are going to be important to note is that other than the feed-forward neural networks, we now want to compute, let's say, the gradient of the loss with respect to h of t. So we not only have to take into account the contributions of the total gradient of the loss at this time step, but we also need to take into account the backward flow of the gradient from this h of t plus 1, because h of t has influence both of h of t plus 1 as well as o of t here in the backward pass. So we also get contributions to the overall gradient of this node from both these sources here. Okay, to start, we will again proceed to compute the gradients of our loss with respect to some node n for every node n in a recursive fashion. And we will start with deriving the loss with respect to the last loss in the sequence. So this L here is the sum of all the losses over time. And if we derive with respect to L at the last time step, all the components in the sum will be 0, but the last loss. And if we derive with respect to itself here, we get a 1. Then we want to compute the gradient of the loss for all the outputs at time t equal to 1 through tau, where tau being the last step in our sequence. So if we take a look at how to compute the ith component of this gradient, then this will turn out to be the ith component of y hat times step t minus 1 with the condition that you see here. And this means that this will actually be 1 for the case where this component I is the same component as the label that we get here. So if we have a softmax and the softmax gives different numbers here as the output, and let's say that the label selects basically this one here as being the right class, then we take the number and compare it to this I that we have here. So this index is then compared to the index I here basically. So if the component of I that we have that we are computing in the same as the one that is selected by the label in this location in the softmax, then we get an additional 1 here. So otherwise this will just be a 0. So it won't, so I won't go through all the details of how to compute this particular gradient. It's not really important to understand all the details of what's coming next. But if you would like to go into more details, then I would suggest you to go through this entire derivation by yourself. Okay, so in lecture 3, we already looked at the chain rule. So I want to briefly recap it again in the vector notation that we will use. So in general, if we have variable z that is f of y with dimensionality r of n, and we have y being a function g of x with x being elements of Rm, then we can compute the partial of z with respect to the partial of xi by summing over the j, the partial of z over the partial of yi times the partial of by j divided by partial of xi. And we can write this whole thing in a very compact vector notation by writing the gradient with respect to all of xi components once in this way. So this is the gradient of z with respect to vector x, and this is given by the gradient of z with respect to y, and then chaining this again with the application of the chain rule with the Jacobian of y here with respect to x. So this is then n by m Jacobian for a matrix of G, and this one we saw is the gradient of Z here with respect to the vector y. So in the backpropagation equations that we will see on the next slides, we will use this quite systematically when we derive the gradient of the loss with respect to some node P to some descendant node D by taking the gradient of L with respect to P as the gradient of L with respect to D and chaining it again with the Jacobian of partial of D over partial of P transposed. So this is the same as what we saw up here, of course. What we want to do is we want to first derive the gradients of the loss with respect to all the hidden activations. And from those, we can then calculate the derivatives of other gradients of the loss with respect to all the parameters that we want to actually change. So we will work our way backwards, and we will start at the last time step tau. And at the last time step tau, this gradient is actually rather simple because we don't have any future descendants of h, which means that no recurrence is applied at the last time step. So here we simply take the gradient of L with respect to the output at time step tau that we have calculated before, and we chain it with the Jacobian matrix here of partial of O at time step tau over the partial of H at time step tau transpose. So if we remember the hidden state H at time step tau, they would be used in the computational of the outputs via the output weights V here. So that's why we get the transpose of the weight output matrix V. Now, of course, we don't only want to calculate the gradient of the loss with respect to the hidden states at the time step, but we also want to compute that for the whole sequence. So then we iterate backwards and we will backprop to the gradient through the time backwards, starting at tau minus 1 up to the very first element in the sequence. And we need to take into account what I mentioned at the beginning when we looked at the computational graph, that each node H of the hidden states at some time step below tau further backwards in the sequence gets two contributions in terms of the gradient from the time step t plus 1 and the hidden state. So this is what we saw in the diagram before in the computational graph. And now in order to form the total derivative, we need to have these two contributions basically sum together to form the full gradient of the last function with respect to some hidden state h of t. So what we do is that we take the gradient of the loss with respect to the hidden state at h of t plus 1, which we compute in the chain rule before. And when we do backprop, and we need to chain it with the Jacobian here. That's the partial of h of t plus 1 with respect to h of t transposed. So what we do here is basically a compact way of writing. So we skip a step in between, but what this really is that this is partial of h of t plus 1 with respect to partial of a of t plus 1, because h of t plus 1 doesn't really directly depend on h of t, but through this pre-activation partial of a of t plus 1. Then we can take partial of a of t plus 1 with respect to partial of h of t here. Okay, so this a of t plus 1 is formed by using the activations from the time step before. So that's basically this part here. So just a compact way of writing this. So this is one contribution to the gradient. The other contribution comes from the output. So here we take the previously computed gradient of the loss with respect to the output at time step t, and we chain it again with the Jacobian here. So it's the partial of O of t with respect to h of t, and this computation of the outputs using the hidden states at time step t is done via the output weights v. So that's why we get the basically the v transpose that we see here. And this part stays basically the same as we have before. And if you look at the first term, then this term here basically also sort of remains the same, this term here. So the gradient of the loss with respect to the hidden state at t plus 1. And basically these two terms that we have here, we get from the Jacobian above. So, and if we look at the first term, then what's coming from this Jacobian is this first W transpose matrix. And this comes from the part, if you remember, that the hidden activations at time step t are used in order to compute the pre-activations of a of t plus 1 by mapping them through the recurrent weights W. So this is why we have this W transpose that we get here. And this particular part here is the diagonal matrix with 1 minus h of t plus 1 squared in the diagonal entries. So this is a big matrix of whatever dimensionality H as, let's say H has a dimensionality n, then this would be a n by n matrix. And so the diagonal entries of these matrix will basically have these terms 1 minus h of t plus 1 squared. And otherwise, we will just have zeros. And this particular form, this 1 minus h of t plus 1 squared, is just the derivative of the hyperbolic tangent. So remember, we have the hyperbolic tangent as nonlinearities, and we map the pre-activation through this nonlinearity. So the outer derivative will be the derivative of the hyperbolic tangent, and together, which gives us the full gradient of the loss with respect to the hidden units. Okay, so now once we have calculated the gradients for all these hidden nodes, then we can use these partials. So these gradients of L with respect to the hidden units in our sequence to form the gradients with respect to the parameters, the biases, and the weight matrices. So similarly, as how we did in the regular backprop, again, we'll take the gradients of the hidden nodes and the outputs, and we will change them by driving the outputs or the hidden units with respect to the parameters. So in the case of the bias weights C, when we take the gradient of L with respect to C, we need to sum over all the time steps because we have the contributions from each time step, of course. And we will take the gradient of the loss with respect to the output at time step t, and we will chain this again with this Jacobian matrix. So this now is the partial of the output with respect to the bias weights. And these bias weights are then used to form the outputs by just adding them linearly. So there is no non-linearity. So then to compute the gradients, this basically just gives us one for the particular output where this component C is used. So in this case, this just gives us once, and this really doesn't change the gradient. So in the end, we can just simply write this as this result as we see here. So if you look at the biases before, the biases B, we can calculate them as the gradient of L with respect to the B's, again summing up over all the time steps T, and now using the pre-computed gradients of the loss with respect to H of T. And then again chaining it with the derivatives of the hidden nodes with respect to the biases. So this part here again stays the same. And again, of course, the biases go into the pre-activation, and these are mapped through hyperbolic tangent. And this is why we get this diagonal matrix here again, which is the derivatives of the hyperbolic tangent on the diagonal. Okay, so very similarly, we get the gradients of the loss with respect to the parameter matrices V. So these are their output weights. Here now we write it a little bit differently. So here we only always consider the gradients in the Jacobians with respect to the ith component of the outputs and summing up over all the i's. So here we take the gradient of the ith component of the output vector with respect to the output weights. And that's just because in order to avoid getting some three-dimensional arrays here. So if we would take this gradient of the full vector with respect to the matrix, this will give us three-dimensional array. And if we want to stay with the matrices and vectors, we can just do this component-wise, and that's just written here. So again, we have to sum up over all these time steps. So we take the gradient of the loss with respect to the ith output component, and we chain it with the gradient of the output component with respect to the parameter weight matrices V, and the output weights. So what does this give us? So this part we have already computed before, and the second part here, the output weights, they map the hidden state at time step t. So they combine with the hidden activations at time step t to form O. Because of that, if we derive this with respect to V, we get the hidden activations of T. And mind you, this is an outer product. So we have a vector of the same dimensions of V as O here. And we have the vector H transposed. So this is an outer product which will give us a matrix, and this matrix will have the same dimensions as the matrix V here. All right, then what we are left with is just computing the remaining gradients of the loss with respect to the other parameters W and U. And the principle is quite similar. So we always have to sum over the time steps T, and we write it component wise just as we saw before. So then we need to take the loss with respect to the hiddens in both cases, and that's these two parts here. And then we chain it with the derivative or the gradient of the ith component of the hidden states with respect to the parameter matrices that we see here. And it's very similar to the case of V. So I will skip the details because we just saw in the previous slides how to do this in the case of V, but it's exactly the same here. But that's how we use backpropagation through time to compute the full gradient of the loss with respect to the weight matrices W, U, V, and the biases B and C. So these are shared over time. All right, now in practice, there's a problem with this standard backpropagation through time. And this is because that the propagation of the gradient through all the previous nodes of h of t when they are unrolled is expensive. And this is also unstable because it leads to vanishing and the exploding gradient. So what can we do about this? So one solution to this is something called as truncated backpropagation through time. And this is really simple. So what we do is that in the forward pass, we compute this for the entire graph that we get. However, now in the backward pass, we will truncate the gradient after some fixed interval. And this is usually aligned with mini batches that you might take. And therefore, we can use now sequential data during training. All right, so as usual, I have some questions for you. So how backpropagation through time really works? So now try to give an intuitive explanation for this. And we would like you to discuss the differences to regular backpropagation. And then I would like you to think about whether we could also use just the gradient of the loss with respect to the network's output at each time step to train the RNN rather than forming the gradient as we have done in backpropagation through time. So where this would mean is that if you use the gradient of the loss with respect to the network's output, we would basically just ignore this recurrent contribution. So do you think that this could be done? And what would be the consequence of this? All right, so this brings us to the end of this video, and I will see you in the next one. Thank you.